We will get harder problems gradually, for sure. All right. Okay. And so this is one of those things that the first 3 or 4 chapters in this course are mostly review stuff, to be honest, okay? From general chemistry, but we'll have a little bit of stuff where I might take you a little more in depth when I talk about it, okay? But you probably know most of this, hopefully. If you don't feel bad. People forget. In fact, the numbers say about 80% you will forget within 3 weeks of any given course. Just, I mean, if you look at it, yeah, like I totally get that from my own experience. All right, so atoms have no net charge. You may remember the atomic number. How many of you remember that that's called Z? That's the symbol for the atomic number. I know that was the end of Gen Chem 1, wasn't it? My goodness. So the atomic number Z, what does that actually tell you? How many protons? Why does that everything organized by protons, though? Anybody know? Periodic table is organized by protons, isn't it? Yeah. So the exactly, yeah. Your neutrons and electrons can vary, right? Your protons are in the middle. They have a lot of the mass, and they're the ones that have the positive charge. So what I want you to kind of think about these as is these are going to be little positive charges spinning around, kind of like planets, right? Just really small. And so what's going to happen is all those electrons that are zipping about around them, their structure, those orbitals they end up in, the arrangements they take on, the chemistry they do, those are all results because of those spinning magnetic fields from those protons in the middle, okay? And the protons in the middle can't move as fast as those electrons can, right? Because they weigh 2,000 times the amount, don't they? Okay? And so you kind of want to think about like this. The orbitals are really just the places the electrons are going to occupy. They aren't actually the electrons themselves, okay? And all of this chemistry is all going to be a result because these nucleuses that have these protons are causing electric fields, and these electrons are going to end up stuck in those. Okay? Is that kind of making sense a little? Okay, it's a little bit of a different way of thinking about that, but it's going to be a much stronger model in your head, okay? And it'll allow you to do a lot more. All right? Now, so the protons plus 1 charge, mass is approximately 1 AMU. Neutrons have approximately 1 AMU, and they're going to have a charge of 0, right? They're actually what's in the nucleus to stabilize the nucleus. The stability of your nucleus depends on your protons versus the neutrons, okay? If you have the wrong numbers of protons versus neutrons, it's not going to be a stable nucleus. It's going to fall apart. That's radioactivity, right? We won't do a lot with radioactivity in this course. If you ever wanted more radioactivity stuff, we do a lot more with that, like inorganic chemistry and stuff. Yeah. Okay, number of protons and electrons are all unequal. This is going to be an ion. If it has a positive charge, that's a cation, right? Anybody ever get those mixed up? I do. Yeah. Like, I've every now and then forget those when I don't teach it for a while. Yeah. The way I remember that is cats are positive. Okay? Most popular videos on the internet? Cat videos. Most popular profiles? Cat profiles. Cats have literally evolved their purr and pheromones to addict humans. So cats are positive. Ants are negative, right? So anions, negatively charged, okay? Why is something positive or negative charge for an atom? Why do they turn into ions? Yep, an imbalance in electrons and protons, right? And what we always do is we do it how far from that it is, right? So if it's neutral, it doesn't have anything above it, plus or minus, because it's neutral, right? You can actually put a 0 if you want. That's how you say it's neutral. Most people don't bother because they don't want to write extra stuff. Okay. If it's +1, what are we missing? An electron, right? +2, 2 electrons. 3, 3 electrons. And so on. If it's -1, we are what? We're actually gained an extra electron, right? So keep in mind, this is one of the reasons I wanted you to think about those protons as these big things, heavy things in the center of an atom, right? So we're not going to gain and lose protons, okay? Because those are what everything's happening around. Realistically, your chemistry all happens around the nucleus, right? Not to the nucleus, okay? Nuclear happens to the nucleus. And so if we have a negative charge, you gained an extra electron, right? If you have a -2 charge, you gained 2 extra electrons, right? And it's just the on balance of those units. Now, what you'll notice is the electrons, again, have a 1/2000th the mass of a proton or neutron, right? And so the masses of these electrons, do you see these in those numbers on the periodic table? Do you see those electrons? It kind of depends. It's a kind of a trick question, right?
I mean, if they're ionic, it's the no. But
So hydrogen, you're seeing electrons.
balance,
Yeah. So you see the electron in hydrogen, actually. It's that 5 at the end. That's actually what gives the last 5 in hydrogen. And you do actually see these in some of these other ones that have very well stated, like BI there. You're seeing the electrons. And the reason for that is once you get up into the 100-ish, around 100, I mean, that's 100 times that number, right? 1, 2, right? And so you start actually seeing electron masses. Are they like determining anything about this? No, not really. They're pretty tiny still, right? But you do start seeing them on the periodic table every now and then. They're not very meaningful for us, to be honest. So we mostly just call it mass is 0, and they're very light and they zoom around everywhere. Okay? We don't really even try to track electrons most of the time, except for, hey, they're bulk moving from one atom to the other, right? And that's because realistically speaking, you can't keep track of electrons. They're popping out of existence. They can literally leap from one circuit to the other and through small barriers. Okay? So trying to pin down an electron is really tough. The last time they did it was like they had a pretty good experiment where they pinned down an electron pretty well and could mostly kind of watch it. Goodness gracious. It was like a $20 million project though. And they spent a lot of money doing it. But it is a kind of cool new technique. So anyways, stuff's happening. So how many protons and electrons does a cation of the carbon atom have if its net charge is +1? So how many protons does carbon have? 6. Very good. How about the electrons? 5. Very good. Yep. 5 is correct. And so there we go. Anybody have any questions about that so far? Okay, how many neutrons does a carbon-12 have, by the way? 6. So there's 6 neutrons in carbon-12, right? Carbon-12 has mass of 12. And so the other 6 mass units, those are the neutrons. Carbon-13 has? 7. Carbon-14 has? 8. Carbon-14 is radioactive. Okay, and that's why you can do dating with it, in case you're wondering. Though it's become much more difficult due to the fossil fuels being burned, because those are depleted carbon, like depleted uranium. Okay, right here is atomic orbitals and shells. You all probably remember this to some degree. I think Viola, Dr. Vincent, or Professor Vincent does the same sort of thing I do, where she shows like the blocks in the periodic table on how to do this, rather than that stupid pyramid that does not work and everybody just messes up all the time. Okay. So the S block is that first block, hydrogen, beryllium, HBe, and that holds 2 electrons in it, right? And then you go over to the P block, which is the next one, which is far on the right, the boron to neon. And those are representing 3 orbitals, each holding 2 electrons, right? And those p orbitals have directionality, because see how they have a directionality to them? Okay. And so you have one in the x, one in the y, one in the z. Right? S orbital doesn't have any directionality because it's not different in any way, in which way you look at, right? And so there's only one s orbital for each period or energy level. And they nest within each other like little nesting dolls. It's a little bit more complicated than that. There's something called nodes. I don't know if you ever got into nodes. And it's realistically, nodes are not going to have like nodes here for this stuff is just not going to come up in our organic chemistry stuff, okay? But we will introduce nodes. Does anybody know what a node is when we're talking about orbitals? Okay, what's an orbital? So I have an energy diagram here of the orbitals, and that's the energy levels, right? This is the orbital for the first energy level, i.e. the first period on the periodic table. So hydrogen and helium are what are filling this one up. And then we go down to the next period on the periodic table, or next energy level on it, and that's this one, right? And see, physically, that's what that looks like. It's just a larger one over it, right? And then we have the next one, 3s, and that's the next period down the periodic table. Now we start filling that one in. And that looks like this, just a larger sphere, right? And they're nesting within each other. Now what a node is there is a nucleus within that, right? And so immediately around the nucleus is what is called a node within the 1s. And it's where you have a 0% chance of finding an electron. Okay? It's literally 0% chance of finding electrons. That's a node. Okay? Where they are not. This right here, this shell, is actually a 90% chance of finding those electrons. So if you're looking for these 2 electrons that are filling this, you have a 90% chance of finding it right there. And that's why you oftentimes see these depicted as like fading dot diagram sort of things, where it like has fuzzy edges. Everybody's seen that, right? Those fuzzy edges have less chance of finding electrons. The darker spots have a greater chance, right? Whenever we look at them this way, we're taking a shell and we're just saying this is the 90% cutoff right there. Okay? Okay. That making sense? Okay. Okay, so the same thing happens with the p orbitals. Has anybody ever seen like a diagram of the Earth's magnetic field? Or ever taken some magnets and played with them with like iron sand? Or seen that where it has like the radial lines coming out? And it makes like this cool spiky diagram thing? Okay. The same thing happens here. This is a monopole magnet for the nucleus. It's positively charged. It's spinning. Okay, so it makes radial fields around it that hold these electrons, right? These electrons are attracted to that magnetic field around it, okay? And so what ends up happening here is you get this shape here, the s orbital, okay? When you don't have enough space for anything else, there's nothing else. You just can't fit more electrons. When you get bigger, you have more space, you can fit more electrons. When you get even bigger, you have even more space to fit more electrons, right? But those s orbitals are super efficient ways of fitting electrons in, right? They just make sense. Like, what would you think of magnets, 2 magnets being attracted would look like? Like an S, right? Where it kind of, you come that distance to the magnet and it attracts, right? Just makes a lot of sense, okay? And so the S ones are the most stable in those. Those are the first filled in. But when you start getting out more, what you actually see is these diagrams, if you start tracing out these magnetic fields, they don't actually radiate perfectly in every direction the same. Okay? And that's why Earth's magnetic field is not uniform. Okay? You start looking at these magnetic fields, they are not uniform at all. And so what you get is p orbitals. That's the next one you get as you got in space. They break up into p orbitals in the x, y, z direction. Okay? And then that's the next most stable places for you to occupy with electrons. And that's represented by over there. Okay? And then what happens is you go down and you go here to this next energy level, right? That's so higher, you have more space, you can fit more electrons in little weird pockets, right? And has anybody seen the d orbitals? Did your book have the actual pictures of the d orbitals?
Yeah, and she had it in our PowerPoint as well.
Yeah. Clovers are a lot of them. They're the x squared minus z squared. Yeah, they're little planar clover-looking shapes, right? Four-leaf clover-looking things. And then you have like a donut with things over it. Yeah. So the d orbitals start looking even weirder, right? And what they're doing is they're actually occupying the non-p occupied space. So the stuff that's not being occupied by the p orbitals, those are breaking up and occupying those spaces. Okay? And that's what you're actually seeing. They start on period 3. Okay? But they don't get filled in until period 4 because they are so high energy and so strange. Notice there's certain desks in this classroom that do not get filled in, right? People don't want to sit up. Nobody wants this desk. Why does that one never get filled in? You can say it. It's right here next to me, right? And then not only is it right here next to me, it has the dang podium right in front of it, and the sink next to it. Yeah, it would be awful, right? It's awkward. And the funniest part is I had a lecture hall once where it didn't have a podium. And so I just had to set my computer and stuff right here. And I ended up with a person that just sat right there. So that entire lecture was like a romantic candlelight dinner. Every lecture. It was like we were the closest of friends. Really sharing some space here. Very intense eye contact. And the funny thing is, I'm actually kind of okay with that, like intense eye contact thing. And so most people wouldn't do that. So it was an interesting experience. But so the d orbitals are very strange and high energy places that have to be filled in, okay? And that's why what happens is you actually fill in the 3d orbitals, don't you, as you go. But you don't fill them in until the 4th period, okay? Now, where do they actually exist? The 3rd period. The 3d orbitals exist in the 3rd period. And so what you'll see is, you guys remember extra octet? We have more than 8 electrons. The ones that started doing that were actually on the 3rd period, aren't they? And it's because they have space that can be occupied by those electrons. Those are the 3d orbitals. They just don't normally get occupied because they're so high energy. Okay? But if you prompt something, if it's energetically favorable to occupy them, they will. Okay? And so we will see chemistry every now and then. Sulfur is a pretty big one. Phosphorus is a really big one biologically. That's how like DNA functions and works. Without that, DNA would not exist. That's how phosphates exist, right? But yeah, even chlorine can do that. It has the extra d orbitals, right? So it can fit electrons in there. Okay. And then we have, of course, the f orbitals, and those are represented below. They don't get filled in. They exist on the 4th period, but they don't get filled in all the way until the 6th. Okay. And everybody knows the lanthide series slots in, right? That's the 6th and 7th. Okay. We basically won't do anything with any of that. The lanthide series, we'll do a little d orbital stuff, but that's about it. Organic chemistry in general kind of just does not use the... Really about the 5th period is where we start being questionable if we're ever going to use that. Okay. So the atomic orbitals are going to be organized into shells. Those are actually referred to as the principal quantum number. Those are all the same thing in principal quantum number, shell, energy level, period. Okay? Those all mean the same thing. They're all the same numbers. That's what those are. Okay? Up to 2 electrons allowed in any orbital. When you increase the shell number, the size and energy of the atomic orbital are both going to increase. Within a given shell, keep in mind that this is a cube root function when you're talking about these things. So you see that these actually are a logarithmic function increasing in energy. So the next one would increase even less and less and less. And that's why metals act like they do. And that's why metals become it when you get low enough in the periodic table. Okay? There are only metals anymore. Because these energy levels start squeezing together really close. Right? Within a given shell, an atomic orbital's energy is going to increase in the following order. We'll have S, P, D, and then etc. F. If we ever get to another periodic orbital, maybe something else will happen. We are, as far as I know, we are actually at the end of the 7th period, and they're still trying to make new stuff. So we may have to add another period. I don't think it's been done yet, but I don't really keep my tabs on that really close. So if it gets done, let me know. It'd be interesting. We'll have to update our dang periodic tables, which stinks. It actually is pretty recent that they finally updated the naming.
I feel like you don't use past the bit period, so
Nope.
do we really need to update it?
Yeah, it's kind of questionable, really, if I'm being honest. Though we kind of do have to update them every now and then because boron and aluminum keep changing whether metals or non-metals or pure metalloids. Every time somebody gets a bright idea of new way of classifying it. So the way in which electrons are arranged in atomic orbitals is going to be called the atom's electron configuration. You all probably remember this a little bit. No? Okay, we'll go over it real quick, like a little. Your ground or most stable energy, i.e. lowest energy, most stable configuration, electron configuration is called the ground state configuration, meaning it's the lowest state, right? Like the ground floor. Okay? Everything else is built off of that. Like if you were to jump out the window, where would you land? Ground. And you would release all your energy, right? Exactly. That's what that is for electrons too, okay? Okay. The electrons occupying the outermost shell, that's going to be the highest energy orbitals, are going to be valence electrons. The rest of those are the core electrons. This is actually an example of that right now. Can anybody tell me which one this is an example of, by the way? Yeah, there's 6 electrons. The thing with 6 protons is carbon. Exactly. And so that's carbon. Perfect. And that's actually the lowest energy state for that. That would be the ground state right there. Okay? Now you'll notice that these are split. Whenever you're filling these in, you always fill them in one at a time. All up first, usually. And then you flip and go down, down, down as you fill those in. Okay? Now, what would happen if I had this go into that orbital right there? That would be what's referred to as an excited state. Okay? This is what happens actually when you have like light hit something. It boosts the electron into a higher orbital. Okay? So visible light tends to do that. Visible light's a weird one. There shouldn't be a visible light. There should be UV and near infrared. Or we should have grouped up part of UV into visible light. But we put visible light because we can see it, and we went humans are special. But visible light in general would do things like that. Okay, they would boost an electron from the 2s up into this 2p, and then when they drop back down, that would give you the line band that you're looking at for that thing, the frequency it emits. Okay, and that's giving you your colors, like my red shirt. Mm-hmm. This core electrons are the red right here. And then that's valence. And the reason that that's important is because your valence electrons are the ones on the outside. If you're going to interact with something, it's the stuff on the outside, isn't it? So the valence electrons do all your chemistry. Okay? The core electrons are held on very tightly, and so they don't really do much. Okay? Okay. Can everybody see the up in energy? Note that these are the energy levels here, 1 to 2. And then these are the orbitals within those energy levels, right? And so these ones right here are really, really low energy compared to these, right? Okay. Now, the other thing I want to point out here is that there is a series that you get some really weird behaviors, okay? And that's the transition metals. So once you get about halfway through and almost at the end of the transition metals, you start trying to double things up in those d orbitals. And that can actually end up with cases where you're like your s electron would boost up into a d orbital. Okay? And you can actually end up with some very strange cases there. Right? We won't do a lot with that, but I want you to know of that. Okay. Does anybody have any questions so far on that? Okay. Pauli's exclusion principle. No more than 2 electrons can occupy a single orbital. 2 electrons in the same orbital must actually have opposite spins. Spins are pretty well represented actually by directionality, but keep in mind that there isn't actually directionality. They're actually opposing magnetic fields, or another way of saying that would be opposing polarities. Okay? And it doesn't even mean that they're at opposite ends of that orbital, okay? It just means that they have opposing magnetic fields, kind of like electricity goes back and forth. Yeah. Think of it a bit like that. So, Aufbau principle. Each successive electron must fill the lowest energy orbital available. So fill them in the lowest ones first and work your way up, okay? This is actually incredibly important, especially for next semester. We'll do some stuff with like nodes and orbitals. That this will become incredibly important, okay? And you'll forget it, and then it'll be one of those things. Hund's rule. This is actually the one that I'd reminded you of before. Before a second electron can be paired in the same orbital, all other orbitals at the same energy must contain a single electron. These same energy orbitals are called degenerate orbitals, by the way. For example, these 3 p's are all degenerate to each other because they're the same energy. Okay? The 2 p's are degenerate to each other because they're the same energy. How about the 2p versus the 2s? Are those the same energy? No, the S is actually lower energy, isn't it? Okay. So these would all be the core electrons. Oh, when I circled it, did I do this one as well? For the core electrons? I might have gotten sloppy when I was circling. Okay, so the core electrons are here. Your valence electrons are up here. Yeah, sometimes I look at you guys when I'm circling things, and it is not a good. It's not the right way to do that. Mm-hmm.
Why wouldn't your 3s?
Because it's not. So one of the ways to think about this is the core electrons versus the valence electrons is actually an energy difference. Okay, and so that energy difference has large leaps when you look at energy levels. And so, for example, pulling this versus this is really a fairly small difference in energy, okay? It would be like pulling her notebook versus her phone, right? Yeah, the notebook's a little harder to pull from your partner, but the phone is a lot easier to pull, isn't it? And so that'd be the phone, that'd be the notebook, okay? Not a huge difference, though. You could do it, right? But the core electrons would be like pulling something out of your partner's bag, right? If they don't want you to pull something out of their bag, you're not getting it, are you? Okay? So you need large differences in energy to pull these. Can it be done? Yeah. But is it very likely in most chemical reactions? No. Very unlikely.
So it stops at the 2 levels?
What it does is it stops at the energy levels. So up to your energy level is where that difference happens. Okay. So for example, if we're just looking at elements, so energy level 1 for nitrogen is core electrons. Nothing's happening to those. They're tightly tucked in. They're stuck. Okay. If we look at nitrogen, energy level 2 is going to be where you have your chemistry happen. Okay. And that's going to be your valence electrons. So another way of saying that is it's your valence shell. Okay. Remember, shells are the energy levels, right? The periods. Is that making more sense? So like if your last filled in shell is 2, or 3 in this case, that has to be your valence shell. Anything on that shell is your valence orbitals and your valence electrons. The 2, on the other hand, and 1, those are all core electrons because they're not on your outermost shell. Okay. And keep in mind that what we're really looking at is these, right? So like this would be these 2 overlapping each other. And so is the p orbital ones likely to be a little easier to get at? Yeah, but like you could get to the s, right? Okay. And it'll make even more sense once we talk about hybridization, okay? Because what you'll see is they're going to mix and make bonds, okay? Those s orbital ones, they're going to get pulled up in bonds. And you already kind of know this because how many bonds does carbon make? 4. And so it uses 2 of the electrons in the p orbitals, right? And the other 2 electrons? Yes, orbital. Yep. There's a lot of this class that's actually just going to be stuff you already kind of know, but you've never really thought about because you just never have time. Yeah. So it's kind of like the results from the other stuff we've talked about before. Okay, write the ground state electron configuration of the nitrogen atom. How many valence electrons does it have? How many core electrons does it have? Okay, so I want you to practice first, try this out, and I'm actually going to come along after you've done this for a minute or so, and I'm going to help you. I'm just going to do it from ground, like the whole thing, okay? But I want you to really give it a good effort and a good try first. You can talk to each other. You can always talk to each other in these and help each other out. Please do. Teaching is sometimes the best way to learn. So. Another way to easily kind of remember core electrons versus the other is that you can actually group up all your core electrons with the noble gas on the previous period. And that's why you do that, is because so little happens to them that you can just represent it as if it's the noble gas in the previous period. Yeah. Your valence electrons have to be separated out because chemistry is going to happen to them. They're going to get manipulated. They're going to get boosted up by light. They're going to do all sorts of fun stuff. Yeah. Unless you have high energy UV radiation or X-rays, in which case you can boost up the core electrons. Do some crazy stuff. Okay. I'm seeing some people got it, so I'm going to just go ahead and go on. And we'll just go from the base of it, okay? So the first thing you kind of want to do is find it on the periodic table, right? And you need a few things to get started. Okay, so like one of the first things you need is how many total electrons are there in nitrogen? Yeah, you can just use the number of protons and then modify it if it's an ion, right? And that's usually your easiest way to deal with that. So 7 electrons, perfect. In what order are the nitrogen atoms orbitals filled? Okay, there's the hard way and there's the easy way. I am not going to even bother teaching you the hard way because it is a stupid way to do it. I'm sorry if anybody likes that way. I have students that argue with me on this every semester I've taught general chemistry. there is a way where you like make a triangle out of it, out of the different orbitals, and then you use that to do the assignment. I have yet to see any student actually successfully do that, ever. Of the 30 students who have argued with me saying that that is the better method. So, we're not teaching that way ever, and we're not using that way. Okay? You actually can do it, correct? Go ahead and use it. I will never teach it. Okay, everybody ready for the actual way it works? Which I'm like 90-something% sure. I remember talking to Professor Benson. This is the same way she does it. Okay, so periodic table, groups 1, 2, that's your s orbitals, right? Okay. Groups 13 through 18, they're your p orbitals, right? Okay. So as you fill in electrons, that's literally what you're doing, is you're filling in the periodic table, okay? And so that's why the shape of the periodic table is the way it is. Once you get past groups 1 and 2, you've filled in all the electrons in an s orbital. The next orbital you need to fill in is p orbitals, right? And so you fill in the p orbitals, and then you can no longer fill any more p orbitals. Go down to the next period, next energy level, next shell, right? We start filling in the next s's, no. And then we have to fill in the next p's because we used up all the s's. And finally, if you get to period 4, it's going to be high enough energy that you can start using those 3 Ds, right? Okay. And the d orbitals are the middle block in the very middle, right? And then your f orbitals would be these ones right here, though we'll never get a chance to do those in this class. Okay? Is that making sense so far? Okay. Okay. So the next thing we're going to do here is we're going to do nitrogen, right? So we have a 1s orbital, and that's the first thing we type out. We go 1s. Okay? And then we're past helium, right? So we know we have to have at least 2 electrons. We can only fit 2 electrons in there, right? And so it's 1s2. Okay? And so now we go to the next thing that exists. That's the 2s, isn't it? Can everybody see that would be the next one we fill? And we're past that, so it's full, isn't it? And so 2s2, right? Am I losing anybody yet? No? Okay. Okay, fantastic. Well, that's full, isn't it? So we need to do the next one. We're still on period 2. We have elements on period 2 right there in the P block, don't we? And so we're going to start filling in the P block. And what we notice is we're how many into the P block with nitrogen? 3, yeah. And so that's going to be 2p3, isn't it? We fill 3 electrons into those 2p orbitals. Okay? Is that making sense? Okay. If we were the next one along, oxygen, 2p, you can just count over in the P block, right? B, C, N, O, 4. If we were boron, 2p, 1. Okay? And that's all you ever do. You just count along. If you happen to have an ion, well, plus positive 1, yeah, you just drop 1, right? So we're at nitrogen. We'd be isoelectronic to carbon. That's it. If we have a -3 charge, what do we do? Yeah, we just move over more electrons in, right? So nitrogen over to oxygen, over to fluorine, over to neon. And so that would be your 2p8, wouldn't it? Okay. Or another way of saying is isoelectronic to neon. Okay. Same electronic configuration as neon. And we have a complete filled energy level at that point. Okay. Which is very stable. You can't have any electrons coming into that because it's as full as it's going to get. Okay. Does anybody have any questions about that right there so far? Okay. Okay, so what's the valence shell? What's the last shell we filled in? 2, yeah. So energy level 2, valence shell 2. That's our valence shell. Okay. What's our core electrons then? Everything else. So energy level 1. Okay. Anything that was energy level 1, that's our core electrons. It's anything not in the valence shell. Okay. Okay. Any questions, concerns, comments, tap dance routines? No? Okay. You better get your party tricks. That'll be the next one. Okay. Covalent bond energy, and bond length. A covalent bond is going to be characterized by the sharing of valence electrons between two or more atoms. This definition, unfortunately, is actually out of date and is now wrong. Last year, it is an equal sharing of electrons. Okay? You can make a covalent bond with one electron now. They're very rare. I'm going to be honest, this definition is good enough for you. Okay? If you want to get more advanced chemistry, then we'll talk about the other definition more, but like it's good enough. Okay? Okay. So you're going to be equal-ish sharing electrons, valence electrons, between two or more atoms. Okay? Okay. Now, this right here is an example of hydrogens coming together and doing this. And what you'll notice is bond lengths are a bit of a nebulous thing. It does depend on energy. Okay? But what you'll see is there is a optimal lowest energy state, which will be what we usually consider the bond length. Okay? And that's where those electrons are in the optimal place between those two nuclei. If you make the bond length longer, the nuclei won't attract the electrons as much. Okay? If you make the bond length too short, they're going to start repelling each other. Is that making some sense? Think of it a bit like a piece of elastic, okay? So you take a piece of elastic and it kind of has that perfect position, right? Where it's stretched out, but it's not pulling, okay? That's a bond length, right? If you go too close together, you'll get repulsions. And that's because the nuclei will stop repelling each other, right? Because they're positives. You get too far apart, and what ends up happening is those electrons start falling off. You stop being attracted as much to each of those nuclei, right? Because they're too far. Okay? If you get far enough, guess what happens? Yeah, you lose your bond. Exactly. And it just breaks it, right? And that's actually what a bond energy is. It's the amount of energy it takes to just break that bond, right? Force them far enough apart that they can no longer attracting. Okay? If you push them together, this is actually a linear increase in energy up to a point. Okay? It does cut off. Almost no book I've ever seen or no professor I've ever heard lecture talks about it, but this does cut off. It does not linearly go up to infinity. Okay? And that's actually what fusion would be. Like nuclear fusion. Yeah. You force them together, it goes way up. I mean, huge amount of energy, so large that this table would not make any sense. You won't be able to see anything else. But after a point, they will fuse and you'll get helium. And then it'll tail off. Okay? After releasing a lot of energy. But you get the point. Yeah, super duper. Keep in mind that like nuclear energy versus chemical energy, we're usually talking like a factor of 100 difference, okay? So compared to nuclear reactions, these reactions we're talking about are very low energy, okay? But compared to like boiling water and doing intramolecular reactions, we're 100 times more than those, okay? So fairly large differences. This right here is a great sort of example of energy diagrams in case you all forgot. So this would be like a ball rolling down a hill, right? And where is it going to end up resting? Down here in the most stable. Now keep in mind that this actually goes the other way too. If you kicked this ball really hard, what's going to happen? It's going to go, bam, and wham, right back out, right? And guess what happens when you try to react two hydrogens but you got them moving too fast? They can bounce off each other. In fact, most possible reactions when they hit each other, they're not in the right orientation, the electrons are not in the right spots, and they actually bounce off each other. And that's why concentration is so important, so you can get more of those events happening. Okay? So keep that in mind that like things all the time come together and just randomly break apart. Okay. Like in an actual sample in real world, these hydrogens every now and then broke apart or started to and then snap back together. Okay. Like that stuff is happening all the time. These hydrogens are breaking apart all the time around you. Okay. Your water is breaking apart to a free radical hydroxide around you all the time. And that's actually the major cause of oxidation, not oxygen in the atmosphere. Okay? I know. You didn't know that, did you? Yeah, yeah. See, that's the geoscience. It's part of my PhD. You get that extra as a bonus content. That's the $10 extra bonus for that. Okay. So this is another great way of thinking about bonds is basically like springs. I'd already kind of hinted at that with elastic, right? And so what you can do is you can actually compress bonds and then they will spring open. They'll hit their minimal energy. That's that same sort of point that if you ever go ding like a spring and it just starts waving around the same area and then finally it fades off. That's that same right here minimum energy state. Okay. And then over here is that other side of that energy state, right? The high energy from springing further apart. Okay. And so bonds typically sort of spring like that constantly. It's called a vibration. Okay. And they're doing that all the time. That's actually what infrared radiation is. That's what infrared radiation does to organic molecules. Okay. And so that's actually what like 5G radiation does to your molecules. It's pretty intense. That's why you don't want to like stand next to a 5G, 6G towers. 6G is just a slightly higher energy one. And so it does it more. But will it cook you? No. And will being far apart from the 6G tower hurt you? No, it's fine. They don't let people close enough to a 6G tower to get hurt in any sort of short term. But I will warn people, if you live next to a 6G tower, the effects of that are currently not known. And there have been indications that living close to power lines, for example, which are a lower energy and lower intensity, actually can affect people's health over the course of like 30, 50 years. Okay. So I wouldn't necessarily recommend living next to it, but if it's between that and the asbestos apartment, take the 6G tower, okay? Just like that's the truth though, right? In reality, it is never a choice of not at all and something that's just everything's better. It's a choice between I don't have enough heat and I'm going to have colder temperatures, or it's too hot. Okay, those are the real choices in life. And if you have that choice, then cold kills 5 times the number of people a year. So choose the heat. Okay, you can get used to the heat. Drink more water. All right. So why is an H2 molecule more stable than 2 isolated atoms? Energy is neither created nor destroyed, right? So these energies aren't created or destroyed. They are maintained. All the energies, all the potential energies, they're all maintained. Okay? So these are 2 individual atoms. And they would have your s orbitals. And they have 2 s orbitals, don't they? Okay? And so when these molecules bond, what happens is they have to create the exact same number of orbitals. Because you bonded doesn't mean space warped and now we have less space. No, that's not what happens, right? What happens is we'll have the exact same amount of space, won't we? Okay? We have the exact same amount of energies. Okay? And so what you see here is that your s orbitals are going to mix together. They're going to make what's called an s bonding orbital and an s anti-bonding orbital. Okay? All the differences there is that this right here is going to be called sigma. Sigma bonding, sigma anti-bonding. They're direct overlap orbitals. They're bonding orbitals or molecular orbitals. Okay? And so we have sigma bonding, sigma anti-bonding. Anti-bonding's higher energy, bonding's lower energy. That's it. That's all that ever was. Okay? Bonding orbital is lower energy, right? Anti-bonding orbital is higher energy. It's the exact same sort of thing, just the higher energy version. Okay? Okay, now, you'll notice that they actually use a asterisk to denote them. That asterisk actually means excited or higher energy state. That's all that ever meant. It was never anything special. You just didn't know it until now. Okay? Now, how many electrons did you have? These, each hydrogen has how many electrons? One. So you have two total, don't you? Now, when you just had a single s orbital, right, those electrons didn't have other orbitals to occupy, so they just were in that base ground level s orbital, right? And they were equal. When we bonded these together, that space in between these became lower energy, and that was the bonding s orbital. This space out here became higher energy because it's not as stable to be at the ends of things rather than the middle, right? And that one went up in energy, okay? And that was the sigma antibonding, the S antibonding one, okay? And so you only have two electrons. How many electrons can go in an orbital? Two. So guess what? That lower energy orbital gets filled. The higher energy orbital takes all the high energy stuff, and we don't have to worry about it, do we? Okay? Why doesn't helium bond? I mean, helium has the same orbitals, right? It has two valence electrons. They're still valence. Yeah. So like neon would be 2, would be the valence shell. And those are still valence and now on the outer. It's just a full valence. Is that making sense? So like helium just has a full valence shell. And that's all it has. So why don't those bond? And I'll tell you right now, they actually do. Like if you put helium, they actually come together, attract, and then split apart all the time. So they like kind of start the bonding process, but never happens. Okay? What would happen with our orbitals? So we have a sigma bonding, right? Sigma antibonding, high energy one, right? Okay, instead of having 2 electrons now, how many electrons do we have? 4. And so the bonding orbital fills up, and then we get to the antibonding orbital, and what happens? It also fills up, doesn't it? And so what ends up happening is we have 2 electrons pulling these things together, 2 electrons pulling them apart. Okay? And we have the exact same amount pulling together and apart, and so they just drift off. There's no energetic favorability here, right? It's not favorable at all. Okay? It's not disfavored either. So helium does actually make like temporary bonds, and this is why helium has some kind of unique properties. Okay? And you can like get liquid heliums and stuff like that. Okay? Or at least liquid-like. It's pretty trippy. But so single bonds are going to be the most common type of bond found in organic molecules. The main difference among single, double, and triple bonds is going to be the number of electrons that are involved in that bond. So single bonds are going to share 2 electrons. Double bonds are going to share 4 electrons, just 2 more, right? And then triple bonds, 6 electrons. Okay. Your bond strength does increase as you go up in the number of bonds, though it is not linear. You get diminishing results. Okay. So breaking a triple bond is not as difficult as breaking 3 single bonds. Okay. It's not the same amount of energy. It's less. But it's still more than a single bond. Okay. It's harder to break a triple bond than a single bond. Triple bonds are also going to be the shortest. Double bonds are the next shortest. And then single bonds will be the longest bond. And you really can kind of figure that out, right? If you take 3 rubber bands and attach them, it's going to hold a lot tighter and shrink it in a lot more, right? And then if you only have the 1 rubber band on your fingers, you can expand them more out. Yeah, you all knew that already. You just never thought about it this way. Yeah. So these are the average bond energies of common single bonds. And what you'll see here is that, remember, bond energies are how much energy it takes to break the bond. Okay? Yeah. And so what you'll see here is as we get more like metal bonds, more towards the metal, lower on the periodic table, we typically get weaker bonds. Okay? As we get more like non-metal character, we typically get stronger bonds. There's a few more caveats in here, but that's what this course is for and why subsequent course exists. So we'll get into those things. These are in kilojoules per mole, by the way. You can convert these to calories per mole as well. So this right here is a single bond energy, single bond length for these different bonds right there. And you notice carbon-carbon bonds are pretty good, nice energetically, okay? They're pretty strong. All right. What you'll note here is these are the double bonds, then these are the triple bonds. Note that oxygen never gets a triple bond. Why doesn't it get a triple bond? Yeah, it only wants 2 bonds, right? Yeah. And it only has 2 free spots in its orbitals. So it can only make and share 2 electrons, 2 bond. Yeah. And then we have nitrogen that can make a triple bond. Carbon and oxygen. Now, carbon oxygen is kind of an interesting one. The triple bond can be made. It's just a very strange thing. So it's a very, very, very weird thing that you will never probably ever see. I'll be honest. Now, here's H2. Again, this is going to just have direct overlap where we're sharing 2 electrons. And that's your typical bond in your mind, probably. Okay? That is a fully covalent bond. They're sharing them equally. Awesome. This right here is CH4. This is an example of something that's starting to become polar covalent, but still single bonds. Okay? And this is going to happen in 4 different directions, and that's that tetrahedral geometry that you may remember. Okay? This right here has 2 double bonds going to carbon here. Can everybody see that? They are not actually overlapping. They actually go like this. Okay? So they're perpendicular to each other. This one right here actually has 3 single bonds, and then it has a lone pair. And that lone pair will be the same sort of orbital here. But what will happen is, let me ask you a demonstration in your mind first, and then you can answer this question easier, okay? Okay, if you're moving a desk out into the hallway, and it's one of these longer desks, like my desk in my office, if you use one person, what happens? You're going to bang all the walls, right? The other end's going to swing everywhere, okay? Take up a lot of space. If you use 2 people, one on each end, what happens? You're much more controlled, much tighter, right? Yeah, you're just localized, okay? And so I'm actually hinting at another concept here. Okay, know that in your minds, localized. There might be something else. Delocalized. And so this right here, these are very localized electrons trapped between 2 nuclei, right? Like 2 people on a desk. This one right here, delocalized. It can move around a lot more, right? And so these lone pairs don't have another nucleus on the other end to keep them contained. Okay? So they're going to spread out a lot more. Okay, so let's talk about the steps to drawing a Lewis structure first, because we kind of need to know that. So you count the total number of valence electrons in your molecule. You write the skeleton of the molecule, showing only the atoms and the single bonds required to hold them together. You subtract 2 electrons from the total in step 1 for each single covalent bond that's drawn in step 2. So each bond you drew, you subtract. You distribute the remaining electrons as lone pairs around the outer atoms first. Okay? Now, I'm going to differ the book's way of doing it and the way you might have heard of doing it a little bit here, because my way, you never have to guess anything. You always get everything right. Okay? Okay. Okay. So we made bonds to things, right? So fill in the center. I'll go ahead and do an example while we're doing this, actually. I think it might be a little easier that way. Okay. So we have like CH4, okay? And so we figure out how many electrons we have, right? And so that's 4 plus 1 times 4, right? So we have to account for a total of 8 electrons. Okay with that? We write in the carbon in the center. Why do we determine carbon is in the center? So you can make the most bonds. Yep. So you always want to figure out what can make my most bonds because I have to bond everything together. Otherwise, it wouldn't be a Lewis structure, would it? Okay. And so I put my hydrogens around it. If I'm not sure what I'm doing, I just equally space them out so I have room. Okay. And then the next thing I'm going to do is I'm going to start with single bonds for everything. Always writing something you can erase because you will need to erase with my method, but you'll always get around. Okay. Now, single bonds, we put those in, and how many electrons have we accounted for so far? 8. And so we have that one done, don't we? Okay. We'll go ahead and do something that has will not finish that easily. Okay. Now we have a little bit of a curveball, don't we? Okay. So carbon 4, hydrogen 1 each, and then oxygen 6. Very good. Total those up, and we get. Do double check me sometimes. I'm trying to do it on the board while explaining things. So. Which is the middle? Carbon. Very good. What do we do with everything else? Surround the carbon, make single bonds. Hydrogen, and we'll put that other hydrogen there. Single bonds. Okay. How many did we use up? 6. Very good. So we have 6 left, right? Do we need any extra electrons to make a full valence shell? You guys okay with noble-like or full valence shell? You understand what I'm saying? If you don't, please let me know. Okay. Don't need any more. Don't need any more, right? Okay. Then we're going to go to the oxygen. Never, ever do the middle until you're done. Okay? Because the middle is where you get to play with things. It's the one that has options, right? All right. So we have 6 electrons we need to use up. And so we're going to fill those all in until everything on the outside is a full valence shell. Okay? And so that's 6 extra electrons on the oxygen to get to 8, right? Is everybody okay with that so far? Okay. Now I look at my middle and I go, that is 6, isn't it? I've used up all my electrons. I can't put any more valence electrons there, can I? And so now I need to borrow electrons from something, okay? This one has electrons I can borrow, right? And so I'm going to erase one set of the lone pair, and I'm going to make a double bond. Okay? And then I'm count again. 8 here, 8 here. That's it, isn't it? Yeah. That's the big difference between my method and everybody else's methods. Is my method, you just keep putting valence electrons in, these lone pairs in, until you have the center filled. Okay? And that way you never have to guess if you have a double or triple bond. You always work your way to it. Okay?
You know if you have a double or triple bond based on where
You don't need to know. If you do my method, you'll work your way to it. Like, we didn't know if we had a double or triple bond at this point, right? All we knew is that it can't have a lone pair and this empty. And so all we did is just move that lone pair in. Okay? And if we had done something like that instead, we'll do another one real quick. And I'll show you that it does not matter at all. You don't need to know anything. Okay? My way, you don't need to know anything about what you're doing. You need to know my method and the periodic table. That's it. Okay? Mine's I'm doing this at 4 in the morning after being awake for 36 hours method. Okay? Because that's literally how I passed my chemistry. I did a double major. It was rough. Okay. Carbons have 4 electrons, so times 2. 2 times 1. And so we're 8, 10, right? And so we write the carbons in the middle because they're kind of equal, aren't they? And we make a bond there. And then we have to fill things around. Let's just do it equal for now because that makes the most sense, right? And so, hydrogen's around. Oops.
This one is.
Yeah, there's one too. You're right. We'll have another example later, by the way. Okay. Okay. So at this point right here, we have all the bonds made, and that's 1, 2, 3 bonds, right? So -6, and then we have an extra 4 electrons we have to do something. Hydrogens are full, so we go ahead and move into the center. Okay. And that's 2, 4 electrons so far. Does it matter if I actually put them correctly on the right ones? No, it doesn't actually. But I just like to do things symmetrically. Okay? And it just makes sense to me to do them symmetrically. Okay, and so what am I going to do now? Well, I don't have enough electrons in each of these, do I? And so what I'm going to do is I'm going to move these into bonds to fill those up to a filled up valence shell. Okay? And so I move that one into a bond, double. I'll move that one into a bond, triple. And why did I do that? Just, I'm filling up my valence shells. That's all I'm doing. I don't know if it's a double or triple. Doesn't matter. That making sense? Yeah, so that's why I have you guys do it in that very, very specific order, right? Is because it keeps you from having to actually know anything about the molecules you're working with.
You know when it reaches when it's full because it has like 8.
Exactly. Yep. You have your full octet. I prefer to say noble-like configuration. No problem at all. Okay, work on this, and next time around, I'm going to expect you to have that answer, okay? I won't give you the minute or two. We'll just dive in. And if you don't know it, I will make fun of you. Heck yes. It will be very light ribbing, not like mean. It will be, my goodness, like you expect me to teach. Disappointment.
Thanks again for letting me sit in on class. I said thank you again for letting me sit in on class.
Definitely.
I'm Jaden, by the way.
Nice to meet you, Jaden. You have a wonderful weekend, I guess.
Thank you, you too.
Probably won't see you around too much because Friday.
Yeah. See you on Tuesday.
Remind me and I'll send you a link, okay?
Okay, gotcha. And I'm friends with Gene, so he can send me the PowerPoints as well. So
Oh, that's true.
that'll make it easier.
In fact, he
for
can
you.
send you the link too.
Yeah.
Just want the whole link.
I did send it.
So yeah, I'm gonna steal all
that's
that stuff.
exactly. Does that work? Yeah, you are of course welcome.
Thank you so
Yeah.
much.
Hi. Hey, Laura.
Hello, our textbook's not working.
We're both having the student set ID. So when I showed you the other day, it pulled it up on a free trial. It told me my trial's over now, so I can't open it up until I get a student set ID, but it says that I've purchased and I have an access code put in.
Okay, so go ahead and go on Canvas, and let's check this out. Okay, I need to stop recording.